In this tutorial, I'll describe some macro and how KERNBASE and PageInfo works. First, what is KERNBASE? KERNBASE enables physical memory access after we enable paging. And this is important because in Lab 1, we enable paging in kern entry.s with these lines. So the CR0PG, that's the enable bit for the paging, and the EAX, so move that to EAX, EAX to CR0, that enables paging. And here, enabling paging means that like all our address will become virtual. So the CPU will never allow you to directly accessing physical address after enabling paging. So that means you cannot access physical address. Then ironically, what I will ask you to you is like then how can you access physical address? So that's important because like the right now we don't know, we did not allocate like how we use virtual to physical memory and so on, but like enable paging, that means like if we just disabled physical address access, then cannot just like access physical address? The answer is no. Then how can he access physical address? Just definitely can access physical address because in Lab 2 you are using that. And let me think about that. Let's think about that. And suppose you need to access physical address 115000. Then if you just directly access this address, then it will never succeed because this now will be translated as a virtual address, so it will go to the page directory and page table, and if that's invalid, then it will generate the triple fault. Then, how can you manage physical page? A short answer is that we will create a direct mapping from virtual to physical, and that's where KERNBASE is pointed. And to give you a better understanding, let's take the following diagram. So on the right side, you can think this small, because I depicted it as a small, because like in default QEMU, we have like 128 megabyte of the physical memory, while we could have full 4 gigabyte 32-bit address space for virtual here. So you can think it as this is a virtual memory and this is a physical memory. And then we have in default like a 128 megabyte of memory, and starting from 0 to 128 megabyte, to enable access, what we are doing is that starting from the KERNBASE to the end of the space. So it's actually 256, but we will just use 128 megabyte because our physical memory size is a 128. So just map this virtual address to 0, another address like this plus 1 page, and then this plus 1 page, and up to like the KERNBASE as a 128 megabyte. And this is basically like what you implement at the boot map region, and then you will actually run boot map region to map this part. And then let's take a look at how exactly this enables a somewhat direct map of the physical memory and how it enables access of the physical memory. So to map a virtual address to the physical address, we will use the page directory and page table. And suppose you try to access like a KERNBASE F0000000. Then we will refer to the page directory and fetch the corresponding page table and F000, and we map that to address 0. So this point will be mapped to here. And if we address next page F0001000, then it will read this one, and then that's 1000, next page, so it will sequentially map from the 0, 0, and up to 128 megabyte. It will directly map to the physical memory. Then it's quite simple. So to access the physical memory, physical address 0, what you need to access is the 0xF all 0. So the first digit is F and all 0 because we mapped the virtual memory to physical memory directly like this. So, and then next page 1000, then we just attach F at the top. Then we can get the physical address, this one. And that's why to translate the kernel virtual address to physical address, we just subtract KERNBASE because we directly map 0 to 120 megabyte like this, and subtracting KERNBASE, we can get the physical address. And the inverse happens, so to translate the physical address to the kernel virtual address, this region, direct map. Because the reason why I call this region as a kernel virtual address, because when you run the boot map region in map-init, you will map this region only available to kernel. That means like you will not set PTEU flag. Yeah, that's why. Because the user we will use in lab 3, they can never access this region. Yeah. So KERNBASE, because its value is like starting from F at the head. So if we get the addresses something like this, starting with F, then it's a kernel virtual address. And then to translate that to a physical address, then just need to delete it. Then you will get 1000 as 1000. And the question from this slide was like, how can he access the physical address 115,000? Then now it's simple. If you want to access 115,000 as a physical address, then add just a KERNBASE, then you will get kernel virtual address, and just add F0. That's it. It's simpler, right? So in just kernel, to translate the kernel virtual address to physical address, then just subtract KERNBASE, and to translate physical address to the kernel virtual address, then just add KERNBASE. And then these operations are, this is actually PADDR macro, and this is actually KADDR macro. Yeah. So something like this. So if you run PADDR over virtual address, and this is macro, and it will be expanded like this, just subtracting KERNBASE. Remove this top F. Then you will get the physical address. It's simple, right? Next, let's recap about Struct PageInfo. Struct PageInfo let us manage free physical pages and also mark which pages are in use and which pages are free with the linked list. And many of you confused about these are physical pages. No, it's not. It's actually a metadata. So it's just like this kind of the array of struct PageInfo. So we have many struct PageInfo structure here, n number of that, and n is equal to the physical number of the physical page as you allocated like the size of the struct PageInfo multiplied by n pages. Yeah, max physical memory divided by like a page size or something, so you can get the like a number of the maximum physical memory pages, and you can multiply with the size of the struct PageInfo. You created these much of like a array using bootlock in lab 2. And this data structure pages array virtually manages each page, each physical page. So for example, so the page struct PageInfo at index 0 manages physical page 0, index 1 will manage physical page 1, and index 3 will manage physical memory, physical page 3, and index n will map to the physical page n, like this green arrows. But unlike page directory or page table, we map virtual address to physical address. In that case, we need to store the corresponding physical page number to the either like a page directory entry or a page table entry. But unlike those which put the physical page number in the data structure, this structure do not have any field that we can store physical address. See, we have ppref, which is a reference counter to keep track of how many usage are there for a corresponding physical page, or how many three pages are linked, we have a pp link. This is a pointer to another struct page info, but how we use for linking the three pages is like this kind of the blue with arrow. Yeah, so we link among these, but we do not have a field to link one of this to the physical page. Then, how can these manages corresponding physical pages like this green arrow, even if we do not have like some of the address mapping about that? And how can we get the physical address from struct page info? We actually use page to PA a lot, page to PA PP, yeah, that a lot, to get the corresponding physical address for a physical page that we virtually manages like with the struct page info. Then, how can we get the physical address of PP from page to PA? And this is done by pointer arithmetic, but don't worry, it's just a plus and minus about the pointer. Yeah. So what that means is that to get the physical address of PP, yeah, we run this page to PA, and if you take a look at the details of the function, so if you follow like the control, like at the right bracket, when you use C tags, so you can take a look at the implementation, then what you will see is it will do pp minus pages and pg shift. Then let's interpret about this. So it first do the operation like a pp minus pages. So pointer arithmetic is just a plus and minus operation, so it's easy, so don't worry. But what this pp minus pages means? So right here I wrote it as like it means physical page number, but why? And then pointer arithmetic is like a special type of the arithmetic operation that you can apply. And how it works is something like, so suppose your pp points to 3. And then if we have a pointer pages, it will always point the start of the array, so it will point 0. And then pp minus pages will return 3. So it actually returns the index of the like a pp. So no matter like what kind of the index it points to, pp minus pages will return the index. And pointer arithmetic is designed like that. So if you have an array, and if you have like one of the element in there, and then if you subtract the starting pointer from that pointer, then it will always return the index. Then it makes sense that like it indicates a physical page number, because we want to have like this index 0 manages page 0, index 3 manages page 3, index n manages page n, so that naturally fits with this pointer arithmetic. And this is how we translate like a pp to physical address. And then right now what we have is physical page number. And the reason why we shift left with the pg shift, and the pg shift here is that if you take a look at the details of this variable again, then it's just a number 12. And left shift 12 means that multiplying 2 to the 12, which is 4096, which is a page size. And if you multiply page number with the page size, then you will get the physical address. And so for example, if you have a pp3, then pp minus pages will return 3. So let's go to the page 3 and then multiply 4096. Then you will get the address of the year, because it's a page number and page size is 4096. And then this is done by this pg shift. So because pp minus pages returns the index of the pp, yeah, that corresponds to the physical page number. So that's why we can get the physical address from PP even if we do not have any kind of link. But to use the address in C, we need to change the physical address to the kernel virtual address. In such a case, we may use page2 KVA, page2 kernel virtual address, PP, and that's actually the same as like a run page2 PA PP to get the physical address first, and then apply KADDR. And what KDDR does is like it translates the physical address to kernel virtual address by just adding KERNBASE. And then you can use page2 KVA PP, then it will return kernel virtual address, so that's why you can use this address in memset. If you just put page2 PA, it will crash because you cannot access physical address. So hope this video clears up your mind about like how the KERNBASE and the direct mapping works, and what is kernel virtual address and physical address, and also the relationship between the struct PageInfo and the physical pages. So there is no direct link, but each of the index in the pages table implicitly links each of the struct PageInfo to the physical page.